All right, so today we'll talk a bit about a little bit more into a lesson 11, which is log linear models for these sort of special types of data, that is square tables. That's when the rows and columns have the same labels. So we're sort of thinking of the same variable at two different points in time, matched data. This kind of is one example, like the presidential approval ratings type thing. Rater agreement, which we'll focus on. So that's, you have two people coding a social science experiment, for example, or you have people rating movies or something like that, and you want to build models of agreement. So we've talked about Cohen's kappa for that, and now we'll do sort of the log linear version and some generalizations. And so the models that we will talk about is this quasi-independence model, which is sort of motivated by some of the strategies for dealing with structural zeros and anomalous data from last time. Symmetry, which is sort of almost always too extreme. Marginal homogeneity, which we've seen before in the presidential data. And this is asking the question of do the marginals change over time? Do the approvals ratings change over time? And quasi-symmetry. Sort of includes these. So the data that I'll use as an example are these movie ratings. So, okay, this is maybe a bit out of date now because these folks are not rating movies anymore. One of them is not even alive, but it's a nice example anyway. So we have sort of three ratings for each movie. We have a table. I'm going to write the main diagonal first, 24, 13, 64. And then the off diagonals, 13, 11, 8, 10, 9. And we looked at this example before, and not surprisingly, independence fits badly for this table. Okay, if it was independent, that would mean that these two raters' opinions have nothing to do with each other. There's no sort of objective quality. And we measured the Cohen kappa to be 0.39. So this was in lesson 4. So this was for a measure of rater agreement. And we said, this had some weaknesses, including that if the two raters agreed more or less all the time, but were sort of shifted, if one of them always gave 1 star less than the other, for example, it wouldn't give a good measure of agreement. And so now we want to take that idea and produce a log linear model version of that. So last time when we were looking at what to do in the case of structural zeros or anomalous cells, we had this idea that we can add sort of slack variables additional variables, and in that setting what we would have these variables do is to match exactly some cell in the table that we kind of wanted to throw out. So we could say something like, these variables are totally independent except for one particular cell that's causing all of the lack of fit. And so what we'll do in the first of these models, the quasi-independence model, is to do this, but we're going to fit an independence model to the off diagonal cells. So in other words, this is a model that essentially is treating the boxed cells, the diagonal cells, the perfect agreement cells, as being the anomalies, and saying that aside from the cases in which they exact agree, when they don't agree, they make more or less independent judgments. So we're saying that it's independence in the off diagonal and perfect fit on diagonal, or sort of saturated on diagonal. That is conditional on being off the diagonal. We have a perfect fit. Another way of saying that is that the odds ratios for the off-diagonal cells are all equal to 1. That's another way of saying that we want the off-diagonal structure of the table to be independent. And so the log linear model for count mu ij will be our term for the overall count, a term for each of the marginals, this is sort of our impossible log linear model. So this is only in the case that I is not equal to j, and we want it to be just a perfect fit for I equal to j. So maybe I should make it like this. And just as we did before, in order to actually fit that model, we create an indicator variable. Diagonals, so something that is just measuring whether these two things are equal, and we get a parameter for each cell. Each cell. So that is our model. Is that the count is given by lambda plus parameters for the two marginals. And then for every entry, a parameter that this is, it gets its own delta, this gets its own delta, this gets its own delta, times this indicator of variables. So we want to fit them exactly. So two questions. So how does this model degrees of freedom relate to the degrees of freedom for just the independence model? So so I have an independence model, has some degrees of freedom, let's call it D, and we have this model, quasi-independence. And suppose I have an I by I table. What are the degrees of freedom here for the model number of, or for the test, whatever you like?
So I was wondering, because we introduced the indicator, so whether that saying we kind of introduce a 1 degree of freedom. So in other words, we're going to say that 50 plus 1.
Right. So for each of these variables, we're going to pick up another degree of freedom, because I'm saying it's the independence model plus I get to fit this exactly, I get to fit this exactly, and I get to fit this exactly. Right? So in this case, well, how many degrees of freedom would the independence model have?
Yeah, so basically it's a 3 minus 1 times 3 minus 1.
Right, that's this one. For independence, and then what do I change about it here? Yeah, so I might have to subtract, so I'm going to subtract 3. Right? So for the test, right? So I have 3. Yeah. So, or I add 3 for the model, right? So I have 3. I've just changed 3. Just looking, every time I add one of these slack variables, I've increased the model degrees of freedom. I've decreased the test degrees of freedom by 1. Right? Okay. So second question. So obviously we want our estimated mu I plus to be equal to ni plus. Right? We want mu plus j, so the marginals for the rows, the marginals for the columns, to match exactly. And then we have this additional requirement that we'd like all of the, so these are the constraints that correspond to the parameters. We'd like all of the diagonal entries also to match exactly. So we think about this log linear model as being the strategy of you take the sufficient statistics that describe your data, and then you match them exactly for each parameter. So that seems pretty straightforward. So can I read off the lambdas directly from the table? What do you think? No, yeah, that's right. So we can't read off it because there's this extra slack variable. So in order to get them to match exactly, right, we're sort of doing 2 things at once. We're moving the rows and columns, and we're moving these slack variables to match the thing. So this will still require like an iterative fit, like a Newton-Raphson or iterative proportional fitting. So you still need your software to fit this. You can't fit it by hand. The table I just erased, actually the fit is not too bad. So like g squared is 0.061 on 1 degree of freedom, and the p-value is 0.94. So it actually fits really, really well. In other words, it says that either they agree exactly or they have completely independent judgments of the quality of a movie, and that's a pretty good fit. So in terms of interpreting the parameters, so the lambdas that describe the marginals are more or less the same. We have odds ratios, so the odds ratios that involve only off-diagonal terms are pretty easy to interpret in the model. Yeah?
Sorry, what does NR and
So these are we talked about these 2 iterative methods. This was the Newton-Raphson, or Raphson, I never remember where to put the H, which is why I abbreviate it. And the other one is iterative proportional fitting. And roughly, this method is just looking at the derivative of the likelihood function and the Hessian likelihood function and doing gradient ascent. And this one is also doing a kind of gradient ascent, but it actually moves kind of, you think of the surface of the model. And it has these natural parameters like exp lambda, exp lambda e I, and so on, like one parameter for each of the rows in the table of sufficiency, matrix of sufficient statistics. Iterative proportional fitting is proceeding by kind of looking at how far off we are and multiplying by errors along each of these parameters. So each of the parameters gets kind of multiplied at each step, and so it's like moving along the surface in a very sort of internal or natural way. So moving kind of linearly in the parameter space, whereas this one lives more in the probability space. Right. So the odds ratios for purely off-diagonal things are completely fixed by the model. They're just always 1. And then we have interesting odds ratios for cells that involve diagonal elements. So like an odds ratio for AB, where I'm just looking at, I have an A and I have a B, I have an A and I have a B, so I'm looking at the little 2x2 table inside the big table, and that necessarily involves AA and BB, which are both on the diagonal. So those things are, this odds ratio is not assumed to be 1. So that's going to be just the count, mu AA, mu BB, divided by mu AB, mu BA. And that odds ratio won't be 1. Tell me what the odds ratio will be in terms of the parameters. So it depends on these. It's the hint. So the part that depends on the total count and the marginals, that's all going to work out to 1. The departure from the odds ratio being 1 is totally captured by these slack variables that pick up the diagonal. So this is a log linear model, so this is going to be x of something in terms of these parameters. Delta, I guess. There aren't too many things it could be, right? We identified A and B, which are 2 of the settings, or 2 of the entries, the values of the variables. So probably it involves the parameter that is related to A and the parameter that's related to B. Yeah, it's 2 deltas. What should I do with the deltas? Yep. So that's the odds ratio that we get. So for example, in our Siskel and Ebert example, odds that Siskel rates con versus mixed is, if you fit it, exp delta con plus delta mixed, exp after the fit, that's 0.96, 0.62, 4.71. So it says that the odds that Siskel rates con versus mixed is 4.71 times higher when Ebert rates con versus mixed. Right, so that's this sort of agreement in the precisely on the diagonals being forced. So like, this tells you that that's quite a large jump in the odds of con versus mixed. So we'll see in a second. So you have to create these indicator variables in the software. I'm not going to give details of that, but we'll see in a second that this quasi-independence model is generalized by the quasi-symmetry model. Yeah.
So right behind you, where we have the degrees of freedom for the quasi-independence, that could be negative. Like if you had a 2x2 table and you're fixing a diagonal, you'd have 1 minus 2, which would be
yeah, maybe I should have said, you're right, this is wrong. Let's add. Right? Yeah. And then subtract the saturated model. And then it'll be okay. We wouldn't want negative degrees of freedom. That would be very confusing. Right? Okay, so here's another model, which is very restrictive. Symmetry model. So we have some kind of symmetric, we have some kind of table which has the potential to be symmetric. It's like I have outcomes x1, x2, x3, x1, x2, x3. And this model is saying that if I have that mu ij equals mu ji. Okay, so not that it has to equal it exactly, in which case there'd be nothing to do, but the underlying expected counts, or the probabilities, are equal. In other words, they depend only on the pair and not the ordering. Of course, if we're looking at a situation where things are changing at all, or there's any difference between the raters, that's a pretty strong assumption. Okay, sometimes it works. Right? So what we want is a log linear model for this kind of symmetry. So we want this to hold, uij equals mu ji, and we want mu ii to be nii on the diagonal. And the marginals should also be equal. Okay, so if it's symmetric, we expect that there's also, in particular, there's marginal homogeneity. Right? Each of the marginals have to be the same if the table is perfectly symmetric. So what does the model look like? Our log counts. But we have some constraints. So we only really have one parameter for each pair of I and j unordered, and one parameter for each of these guys. So there's no difference between x and y, between Ziskel and Ebert in their distributions. So then we use, as usual, like a g squared fit. In this case, the degree, in the Ziskel and Ebert example, the degrees of freedom for the g squared, the test degrees of freedom is 3. And we would get, around the model, we would get 0.059, which is on 3 degrees of freedom, is of course a very good fit. So, okay. So there is the appearance of, although it's a fairly assumption, there's appearance of symmetry, so it doesn't say that they're independent. Of course, they're very far from independent. They agree very often, or the quasi-independence model wouldn't fit so much better than the independence model. But what we're saying is that these raters are indistinguishable, essentially. We could switch the names, and we wouldn't see any real difference in the results. And from a constraint point of view, these MLEs will look like our estimated counts, of course, are the same, whether we're looking at ij or ji, and that's basically just the average multiplicatively. No, I think I want to add those. With the rest of the things having more or less the same interpretation. And it's a little, if you're not using a prepackaged function, of course, it's a little fiddly to force this into the code for an SAS. You need to figure out how to express that you only want parameters for each diagonal cell, and one parameter for each diagonal cell and one for each other pair of cells. But there's in the online notes, it walks through how to create how to set up this model, if you'd like to. Okay, so there's another model which kind of generalizes these two, which is called a quasi-symmetry model. So we want to do something which allows sort of both of these things to happen. And so it's kind of like a symmetry model, but without requiring that the marginals are the same. And let's see what that looks like. So the counts, we have an overall, we have separate marginals allowed for the rows and the columns for Siskel and Ebert. And then we have a sort of dependence term. And we're just imposing that this dependence term has symmetry. Right, so it's like, okay, we have this one which is total symmetry, and then in this we're just relaxing the idea that the rows and the columns are the same, but we're still requiring that fixing that sort of, or allowing for the rows and columns to be different, so sort of having an independence model on the rows and columns, the structure of the interaction is symmetric. So it's like the dependence being symmetric without the counts being symmetric. So special cases of this happen, or the two things we just saw are special cases of this when some of these parameters are simplified. So that is, the symmetry model was exactly this, but with the additional requirement that the marginals are the same. So symmetry is quasi-symmetry with the requirement that the marginals are the same. And independence is just setting the independence model, not the quasi-independence model, but the independence model is just setting these interaction terms to be 0. As usual, the degrees of freedom is the test degrees of freedom. It's the saturated minus the number of parameters in this, and that works out to be I minus 2, I minus 1 divided by 2. And to fit it, we just take the symmetry model and we add in these guys. So this was the symmetry model plus these two. And in our example, this one fits great too. On 1 degree of freedom and p-value of 0.93. So the other sort of special model for this sort of table is this marginal homogeneity model. Yeah, sorry.
That G squared, are we supposed to be suspicious of that? Like, because that's such a good...
Because it's such a good fit?
Yeah, from that one homework where we...
That maybe we made up the data?
Yes.
Yeah, sure. It's a little suspicious, right? It's like,
I didn't know we should...
Yeah. Maybe they got lazy and they stopped watching they didn't watch all the movies. They split it up and they were like, you watch that one, I'll watch this one, and more or less rate it the same once in a while.
But that's like something we should be, I guess, or is it, because it's a log, because that was like with the Kai's.
Yeah, right. Like the Mendel stuff, right, where we said that if a fit is too good, then it's reason to be a little suspicious.
Like a log linear, I mean, is it the same case? Where
Yeah, sure. I mean, I think that's perfectly reasonable to be a little bit nervous. I mean, it's could be, of course, it could happen, but
Right.
but if you have other reasons to be suspicious, that seems pretty reasonable. Okay, so marginal homogeneity. The idea of marginal homogeneity is you want to test are the rows and columns really the same? Column marginal is the same. And for this, there's not a direct log linear model, but the models that we've proposed so far, some of them sort of differ only by this, right? So in other words, you can think about symmetry. A model which is the symmetry model is one which has quasi-symmetry. Symmetry. And then we also impose marginal homogeneity. So take this model and add marginal homogeneity, we have a symmetry model. So that means that if we just want to test marginal homogeneity, we can test it by comparing these two models, right? Comparing the symmetry model and the quasi-symmetry model. And the difference, the delta G squared, is its test statistic for marginal homogeneity. Right? Because that's the additional constraints that we had to add to go from one model to another. Symmetry versus quasi-symmetry, the delta G squared. So our delta G squared for marginal homogeneity is just the G squared we get from fitting the symmetry model minus the G squared we get for the quasi-symmetry model. And the change in degrees of freedom will be I minus 1, or the test, the change in degrees of freedom. And so in our example, the G squared for this will be 0.587, which is 0.5928 minus 0.0061 on 2 degrees of freedom, and p-value of 0.746. So that homogeneity model, the idea that these marginals are equal, fits pretty well, which is no surprise, kind of, because the symmetry model, which is fit pretty well. So, okay, so quasi-symmetry is the most complex, and then we can get symmetry or independence as special cases. Let me just do a summary table, and we'll stop this. Okay. Model, degrees of freedom, G squared, p-value. So we have an independence model on 4 degrees of freedom, which fits terribly. We have a quasi-independence model, which is on 1 degree of freedom and fits suspiciously well. We have a symmetry model on 3 degrees of freedom, and that fits okay. It's 0.94 small. Marginal homogeneity model on 2 degrees of freedom that fits okay, 0.75. And a quasi-symmetry model on 1 degree of freedom, which also small and also 0.94. Okay. So no matter how you measure it, more or less in this example, they agree well. You can certainly imagine a case where these shake out differently, and I believe there's an example of that available in the online notes. Okay, so let me take a break and ask if you have any questions. So this more or less finishes the core material of the class. What's left in the next sort of 3 or 2 lectures before you guys start giving your presentations, I'll just be doing some topics type stuff. If you have any special requests that are related to your projects, please let me know, and I can shift. If I don't hear any special requests, I'll probably spend most of next week talking about missing data, which is sort of not in the online notes, but I think it's something that you are quite likely to have to deal with. Any questions before I go on? And the thing that I'm going to talk about for the rest of today is to revisit graphical models a little bit after what we talked about last time. Okay, so we've sort of talked around graphical models, and perhaps it's a good time now, especially given the discussion we were having last time about this idea of separation. Right? So last time we were talking about this separation and collapsing categories in the right, when can I know that I don't have an instance of Simpson's paradox? Right? If I have like x, y, z, if I collapse over y and I have the conditional independence x is conditionally independent of y given z, I could easily get a case of Simpson's paradox. If I want to collapse x or collapse z, so sort of contract away part of this table that depends only on the rest through that variable, then I don't have to worry about it. Right? That's what we said. And so the graphical models kind of expands on this idea. So these things were developed initially in the 1980s by especially Pearl, Lauritsen, and many others. And they share kind of a common origin with like statistical physics models, like Ising models, if you've ever heard of that. Models of sort of materials where you have magnets flipping back and forth or other sorts of dependent structures. And the idea is that we can make a explicit connection between a sort of a visual combinatorial object, a graph, and a set of probability distributions that are associated to the graph. So there are two main types of graphical models. The ones that are most closely related to or that are examples of the log linear models we've discussed are called undirected graphical models. The other type, or one of the other types that's most common, are called directed acyclic graphical models, or Bayesian networks. Now both of these can handle both discrete data, like we're talking about in this class, and continuous data, or mixed discrete and continuous. And there are other types of models that set up dependent structure in different ways. But of course, we'll focus on the categorical or discrete case. So we have for example, the undirected graphical model that looks like this, ABC, corresponds to the hierarchical model AB, BC, the hierarchical or log linear. And if we explicitly write in the factors as boxes, it looks like that, A, B, C. So these sort of represent the parameters, like a lambda AB, and it has an index for each value of A and B. And this one is the lambda BC with an index for every value of B and C. And these things represent the state. And there's a conditional independence relation, which is A is independent of C given B. And in these, we have this problem of normalization that I mentioned last time, which is that if I allow these to be arbitrary parameters, I have to figure out an overall parameter that matches it, or if I'm interested in the probability distribution, I have to figure out this partition function, this correction factor that allows me to make sure that the probability distributions that I get out sum to 1. Just to show you what a directed graphical model looks like. That's similar. We could have a variable B, variables A and C, and there's a directed graph on these three variables, and it has associated to it a directed factor graph, like B. You could think about there being a factor up here that represents the root distribution on B, And then we have kind of transition matrices from B to A, and a transition matrix from B to C. And this one also satisfies A independent of C given B. But whereas in the undirected graphical models, I can more or less read off conditional independence by this kind of graph separation rule, is this separated by that, in the graph by the rest of the graph, the reading off conditional independence relationships from a directed graphical model is a much more complex criterion, which is called D-separation, and I won't tell you how that works, but just be aware that it exists. And not all of these correspond to hierarchical log linear models. So this is kind of a factorization of a probability distribution, ABC, probability of B, some probability here that's unconditional, probability of some A given B, which is in this matrix, probability of C given B, which is in that matrix. So the rough idea you want to think is that undirected graphical models are kind of built from marginals or built from the result of applying a sufficient statistic. Directed graphical models are built from conditionals. And we know something about the conditionals, we want to model the sort of the causal relationships more directly. Okay. So let's make a careful definition of undirected graphical models. So what's an undirected graph? Undirected graph G is a pair VE of vertices V and edges E, both of which are just sets. And for us, these vertices will correspond to variables. And the edges, so what the edges mean is a little bit subtle. You should think about this as being an association, or more precisely, a lack of conditional independence. An edge, the absence of an edge indicates a conditional independence. And vertices are adjacent. If they have an edge between them. And a path between two vertices is a sequence of vertices x1, x2, xn, with each pair xi, xi plus 1 adjacent. Just what you would think a path is. I follow edges through the graph. And when we're relating a graph like this to a hierarchical model or a log linear model, an important concept is the idea of a complete graph. Graph is complete if there is an edge between every pair of vertices in the graph, or a subgraph, a subset of the graph. So here's a complete graph. Here's a complete graph. Here's a not complete graph. Here's another not complete graph. And if I take a bigger graph, this one, and I take a subset of the vertices, so I choose some of the vertices, like say I choose this vertex 1, 2, and 3, a subset of vertices together with the edges that are induced, that exist already between those, is called a subgraph. Vertices plus any edges involved, or any edges among them. And as you can see from this example, you can have a graph which is not complete, but it has several complete subgraphs. That's a complete subgraph, that's a complete subgraph, that's a complete subgraph. So it can have complete subgraphs, and those subgraphs can overlap. And it's the complete subgraphs that correspond to maximal factors, or factors, just factors. All the complete subgraphs corresponds to a lambda, or a factor that appears in the hierarchical model. So the key miracle of undirected graphical models is that we can relate conditional independence to separation in the graph. Is approximately the same as conditional independence. So what do I mean by graph separation? So if I have A, B, and C, distinct subsets of the vertices, we say that C separates A and B. So a subset of the vertices separates another subset from another subset if every path from a vertex in A to a vertex in B intersects a variable, a vertex in C. Okay, so that's a precise version of what it means for separation to happen.
So the separation implies conditional independence? That's at the top.
Well, I'll say under what approximately, that's the idea. Okay? It's not literally true in all cases. The literal situation is slightly different, but that's more or less what's going on. But we should be careful about exactly what's true. Okay, so examples. So I could call this thing A, I could call this B, I could call this C, and I have this graph. So B separates A from C in this case. If I added another thing here, that would no longer be true. Okay. And graph separation has kind of a set of implications. For example, if x is independent of y given z, in other words, x and y are separated by z, then y and x are separated by z, so it's symmetric. If x is independent of y given z, or z separates x and y, and u is some function of x, then u is independent of y given z. I'm sorry. These are actual. These are also actual conditional independence statements. Let me come back to that. But it's possible, if you can imagine, some separation properties to be deduced from other separation properties. But one of the subtleties is that there are probabilistic, like things you can deduce from conditional independence relationships that don't correspond to graph separation. So to answer your question, yes, if the variables are separated in the graph, then they're conditional independence, but they can be conditionally independent without being separated in the graph, depending on some detail situation. So in some sense, like a pathological situation, that can happen. Suppose we want to go in the other direction. So we want to encode conditional independence relationships. We know conditional independence relationships. Okay, we did some tests in the graph. So we start with some random variables, and we know certain conditional dependencies hold, and we want to encode them in the graph. So we want to construct a graph. Okay, so we start with the graph, obviously. One vertex per variable. We said it was the lack of edges that indicated independence, so we omit the edge between each pair of variables if they are conditionally independent given the rest. So say x and y are independent. I have x is independent of y given the rest of the variables. I can sort of think of this being a forbidden edge between them. Whatever the rest of it's going on, they're connected, and I don't draw that edge. So this defines a graph. If I do this for everything, it defines a, and the rest of the edges are allowed to happen, a pairwise Markov graph. So for example, suppose I have the statements x is independent of y, given zw, y is independent of z, given ab, given whatever is not x, sorry about that, xw. So we have 4 variables, x, y, z, and w. And we're saying we're going to forbid this edge, and we're going to forbid this edge. So the resulting graph, x, y, z, w, would look like this. All the edges except the forbidden edges. So this graph is encoding a set of pairwise conditional independence statements, one for each of these excluded edges. And what other conditional independence statements hold? Like we didn't, this isn't necessarily all the conditional independent structures that hold among the variables. So one of the results is that you can read off the rest of them from the graph. So you could say that's a theorem. Let G be E be the pairwise Markov graph, so constructed in this way, for some distribution P. Let A, B, C be distinct subsets, not just vertices, of V, the set of vertices such that C separates A from B in the graph, in this pairwise Markov graph. Then we can conclude that this whole set of vertices, or this whole set of variables, is independent of all the variables that are in B given C. So that's a probabilistic statement about conditional independence. So if you drew exactly from this table, if you had a table, a set of probability distributions that came exactly from this P, that conditional independence would hold exactly. And note that, if I can say, if A is separated, could certainly be separated from B by the empty set, that is, there's just no path between them at all, so it's sort of an empty condition, then we write that as A is independent of B. And I would say that just the independence hold. All we need to know about is the row and column sums, where the rows and columns are defined by the variables in A. So in other words, given the graph G, I could say M pair of G is the set of probability distributions that satisfy this pairwise Markov property. That is, P is in a probability distribution satisfies the property, or is in the set of all distributions that satisfies this property according to G, if in this probability distribution, X is independent of Y, given the rest, if and only if there is no edge from X to Y. And then there's a global Markov property, which is the set of distributions satisfying that P is in M global if, in the case of this probability distribution, A is independent of B given C, if and only if, that's that one, if and only if C separates A and B. A and B. So what we're saying is that the set of all probability distributions that satisfy the pairwise Markov property on G is equal to the set of ones that satisfy this global property. So for example, you also get Y is independent of Z given W in that example. Well, not quite. But. Okay, so let me talk about how that relates to the parameters or the parameterization. So I said it was sort of all about complete subgraphs. So a complete subgraph of a graph G is called a clique. And a maximal clique is one that stops being complete if I add another variable. So for example, suppose I take this guy. That's a clique. It's a maximal clique because if I add that variable, it's not a clique anymore, but it's also true that just one variable is a clique. These three variables are a clique. These two variables are a clique. These are just not maximal because I could add another variable and still have a complete graph. Okay. So we want, in sort of a hierarchical model, the most important terms of the model correspond to the maximal cliques. Then we have sort of additional terms for the sub-cliques. So a potential is a positive function of discrete outcomes of the variables. E.g., 0, 0, 0. Let's make that phi instead of C. 0, 1, 0. And all of these things are positive numbers, and they depend on x, y, z variables, x, y, z. Maybe these are binary variables. So a distribution, probability distribution, factorizes according to a graph G. This is a definition. If there exists potential functions call it C of X restricted to C, where C is a clique. one per maximal click. Such that the probability distribution, so if I list out all of the outcomes of all the variables in my graph, that's equal to 1 over this partition function that we talked about a little bit last time, times the product over all cliques C, potential function applied to the state of those variables. Okay? So this is kind of the multiplicative way of writing a log linear thing. The Z corresponds to the lambda, and these correspond to maximal cliques, or maximal parameters in the log linear model. So the main thing that sort of makes the whole graphical model's idea work is called the Hammersley-Clifford theorem. The Hammersley-Clifford theorem says a positive probability distribution, that is a probability distribution in which it has no zeros in it, so there's no zero cells. So every pi jk is strictly positive. Satisfies what we just talked, the property we just talked about, the pairwise Markov property. Markov property with respect to a graph G, if and only if it factorizes according to G. Okay. So we've kind of been using that implicitly whenever we draw a picture of a log linear model. That we've been switching back between saying we can talk about the parameters or we can talk about the dependent structure in terms of how diagrammed by the graph. And the result that makes all of that, this is the result that sort of makes all of that work. Okay. And it's unfortunate that it has this requirement that it only works for positive things. And that's kind of why I often have sort of a caveat when I'm talking about this, because if we allow for zeros, that this theorem doesn't hold anymore. It's not if and only if anymore. And this was a big issue for the people that came up with this theorem. So they came up with this version of the theorem, and they spent almost 4 years trying to find one that doesn't have this restriction. And then they finally gave up, because it's not true without that restriction, and published that. Okay, so let me say one word about the directed versions, and then we'll be done with this sort of topic. And if you're interested, find graphical models interesting, I encourage you to look at it. Especially when you come to a situation where you have a lot of variables. And it's not practical to enumerate all of the hierarchical models. So let me say one thing quickly about Bayesian networks, or directed acyclic graphical models. So a directed graph is one in which each edge is not just an edge, but it has a direction. And so one of the results of that is that every vertex has a set of parents and children, right, which might be empty. And it's acyclic. Acyclic means that it doesn't have any directed cycles. So here's an acyclic graph. Even though there's an undirected cycle, there's no directed cycle. I can't follow the arrows and get back where I started. Here's a cyclic graph. So these are the ones that I'm not allowing. They're disallowed. There's similar types of ideas for factoring according to a graph or being Markov according to a graph. And we would say that P, probability distribution P is Markov to a directed graph. If the probability of some outcome on all my variables is equal to the product over all variables of the probabilities of that variable given the state of its parents. Okay, so we're saying this is a kind of probability distribution which, instead of being built on these sort of sufficient statistic or marginals, is built on conditionals. You're looking at the state of the parents versus the state of the children. So let's see an example. This is sort of a famous smoking example. So suppose I have overweight, smoke, and I'm trying to predict heart disease and coughing. And maybe we have the model that smoking and overweight predict heart disease and smoking predicts coughing, but otherwise they're not related. So what we're saying here is that probability of overweight, smoking, heart disease, and cough factors as probability of overweight, which is sort of a root distribution, probability of smoking, so those sort of are unconditional, times the probability of heart disease given overweight times the and smoking, because it has two parents, times the probability of cough given smoking. So that's the hypothesis that that graph translates into about the probability distribution. Another example, if I have, say, this graph, x, y, z, w, x and y both have arrows to z and z have an arrow to w, we'd say that a probability distribution that comes from this graph would have the form the probability of x, y, z, w is the probability of x, probability of y, probability of z given x, y, probability of w given z. So it's a product of a bunch of probabilities that come from that. And again, it's always true that in terms of conditional independence statements, one of the statements you can say is that w is independent of rest of the variables except w itself and its parents, given its parents. There are other conditional independence statements that you can read off, but that requires this more complex criterion of D separation. Okay, so I'll stop there. I'm not going to say really anything else about graphical models. And next week I'll talk about either whatever you ask me to talk about. If you ask me nothing, I'll talk about missing data.